Good afternoon, everybody. I'm Srividya Iyer, and my team and I have been working on machine learning for networking applications. My prior experience is in network architecture and engineering for over 15 years, so I have seen the good, bad, and ugly of networking. So, get started. How do I do this?
Can you guys help her?
Oh, sorry. So why machine learning for networking, other than the fact that everybody is using machine learning for every application and claim that it can do everything. So there's really two reasons for it. One is, as we saw in yesterday's presentation, the network is changing and has changed. The network traffic has changed. So we need new mechanisms to figure out how network is working, to get more visibility into the network. And the second thing is all these new devices and new networks have a lot of data that's hard for human brain to process. So if you have to process data from multiple sources and try to find patterns in them, it's really difficult. So machine learning comes in handy to do that. So, oops. I think I did the, oh. Am I pressing the wrong one here? Okay. Okay, sorry. What does building a machine learning application involve? So it involves four distinct steps. The first thing is framing the problem, preparing data, training the model, and using the model. We are going to primarily talk about framing the problem and preparing the data, because building the model and using the model is nothing specific to networking. It's pretty much same to any machine learning application you do. When we started doing this, we thought, oh, we already know the problem, we already know network data, so we were thinking we were going to be using some cool algorithms, and that's what we are going to be spending all our time with. But mostly what we ended up doing was trying to figure out what problem we are solving and trying to figure out what data and how to actually process the data to feed into the algorithm for it to actually learn the correct thing. So we spent about 75% of our time just processing data and framing the problem. Once we got that, the algorithms have been around for a long time and they're pretty robust. So we didn't have any problem getting there, but just dealing with data was the main problem. So what does framing the problem mean? In machine learning, there is two sets of problems. One is you provide machine learning with some data, and then it says, okay, give me the groupings of data. So tell me what the relationships are between the data, and then figure out the pattern. So that's your clustering model. And then the second model, the second problem that you're trying to address is to predict the outcome of future events, and for that one, you actually give the machine learning model some insight into it, and then say, okay, what did you learn from my insight, and tell me what you are seeing from the data. So the first one is your unsupervised learning, which means you just give data and then it does what it does. The second one is you're sort of providing some kind of supervision for the machine learning application, so it sort of learns what you're trying to tell it to learn. So the reason the problem definition is so important is because that determines what type of data you collect, how much data you collect, and what it is that you're trying to make the algorithm do, and what type of performance metrics you're looking for the algorithm to do. So the data collection was one of the hardest and the most tedious things we had to deal with. Most of you who have worked in networking know that the vendors' devices, even though they are standardized, they don't necessarily give out the same type of data. There was data formatting issues. So we spent a lot of time trying to figure out how to collect the right data. So there's actually two types of data collection. One is your offline data collection, where you collect data over a period of time and then use that data to train the model. And then there is the online or the real-time data collection. There's still no good methodology that actually does real-time machine learning model update. You could aggregate it for 30 minutes or 1 hour, but there's no like really real-time model update in machine learning, or at least not for networking. Maybe there are other domains that are able to do it, but it's really difficult to do real-time updates for networking data. So some of the data that we looked at was flow data, packet captures, firewall logs, syslog, telemetry, though we realized a lot of the streaming telemetry was a lot more hype than we were actually able to get anything out of. So if anybody has any insight into it, I would like to hear it. We looked at device configurations and some topology data. So the next thing that we had to do was feature extraction, and this was also the most tedious and really difficult aspect of doing the machine learning for networking. This involved knowing the domain. This involved knowing what type of features or what attributes really gave the good insight, because as you can see in a packet, let's say you're doing a packet capture and you have a lot of features that come out of packet capture in the multiple layers, but not all data is created equal. Not all attributes are created equal. So trying to figure out what features actually worked was, part of it was domain knowledge and part of it was just trial and error. We had to try different permutation combinations of features. So this is again the most tedious and part of trying to figure out what data to feed into the model. So if you feed in junk, you basically just get junk models that doesn't actually do anything. So it's really important to get good quality data. So the next part is training the model. There's nothing really specific about it. This is a common 70-30 split. So 70% of the data is used for training the model and 30% is used as for testing. One of the things that I do want to stress is the need for spatial and temporal diversity. So we could get data for 2 days and train it, but that's not really giving you the temporal diversity. So you have to collect data over a period of time, sample it, and then do aggregations, and then train it. And for the spatial diversity, we had to take data from different networks because not all networks are created equal. That's also one of the issues with using networking data for machine learning. Once the model is trained, then you need to verify it for performance, and the performance also depends on what type of application you're doing and what really needs to be resolved from that application. And there's really no way to distinguish any learning algorithm as best. Again, it's trial and error of which algorithm works best for which application. So in the next 4 slides, I'm going to talk about some of the common networking problems that can be used used in machine learning. One of the things I don't include here because we haven't really done anything with it is routing analysis. What we have done is traffic classification, traffic prediction, anomaly detection, and fault event detection. We haven't done a lot of it in all of them, but at least we have attempted some of these application. So the first one I want to talk about is the traffic classification. So classifying traffic, current methodology is basically port-based or payload-based. Port-based with non-standard ports, you're not getting what you need. And because we saw 85% of the traffic is TLS, it's all encrypted, so looking at payload is not an option either. So this is a really good application for machine learning, because what it does is you look at flow data or packet header data. It tries to look at some of the other fields. And one example was, we didn't realize we were doing P2P applications. BitTorrent, apparently the first packet is 66 bytes. Somehow it picked up that it was 66 bytes and said that was BitTorrent traffic, and it ended up being BitTorrent traffic. So it sort of learns from its environment or its context, and that's one of the nice things about using machine learning for it. That's an advantage over current methods. We tested it on support vector machines, decision trees, and random forests, and each algorithm behaves differently. And I'm not going to go into detail, but I do have some background slides on what these algorithms are. So if you have nothing better to do, you can go back and look at them. So. The next application we looked at was traffic prediction. The current method is typically time series analysis. We didn't do a lot of things with it. We just took a sampling of data and we tried to use artificial neural networks. And this is one of the things that I am looking for. I've been talking to some of you, and I'm looking for some use cases to test and try out some different algorithms. So I don't have a lot of insights on this one. The next one is anomaly detection. This is to do DDoS and malware detection. Again, this one, the research is typically using k-means clustering. And what it does is it identifies most of the common things that you can see, but a lot of the corner cases, which DDoS ends up being a lot of corner cases, it doesn't really detect. So this is another area that if any of you have use cases I'm looking for. I think what would be really good is some kind of hybrid methodology where you cluster to kind of differentiate the traffic and then do some kind of supervised learning where you give it a lot more than what a typical clustering application does. So. Fault management is the one that we have been working a lot on. So this is to accurately predict network faults that are kind of flying under the radar. Most of you who have worked in networking know what happens in a network fault. Somebody complains that the network is not working. So you have to go and figure out where the fault is, so fault isolation, and then you have to run around trying to mitigate the fault. So one of the nice things about using machine learning for that was looking at historical data. We were able to, and this is the one area that we actually saw some good results. We were able to see a lot of patterns in the data over a period of time. So all these faults just don't happen overnight. There's a lot of underlying symptoms that are there, and the machine learning algorithm was actually able to detect some of these underlying patterns. So even though the fault didn't really actually had occurred, but there was a good probability that fault was going to occur. So you could predict and say, yeah, this is, you're seeing a lot of, say, for example, TCP duplicate acts. Then you can say, you know what, maybe there's some problem with your link, and that's why you're seeing so much latency. And so those kinds of patterns we were able to see. And this was one of the ones that I was really excited about, because you could actually see things that you don't have to wait until something breaks, and then you're scrambling around trying to isolate it and find it. So what does building a machine learning infrastructure mean? is you need your data collection. So you need to set up your device, set up taps, port mirrors, flow monitors, or anything else you need. We primarily used open source tools. If you already have data collection sort of framework in your network, you can use any of the commercial tools that can get syslog data or packet data or any of the flow data. The second piece of it was feature extraction. Like I said, this was the most tedious and hard thing to do, and you really needed domain expertise. So if people are thinking machine learning is going to suddenly solve all problems and we won't need any more network engineers, this is what proved us that no, because you still need to understand how networks work to be able to train the machine learning model accurately for it to actually do something. So we used Python, pandas, and NumPy to do a lot of the data pre-processing and munging and getting features and things like that. I don't know. There are some commercial tools that does feature extraction, but most of them are very expensive and they don't really work that well for networking data. So I don't know. I mean, you could probably try it, but I don't know if it's very effective. The third part is the algorithm selection. Even though there are papers written that says, this algorithm performs well for this type of data set. If you vary even one or two attributes, it completely changes. So this was basically trial and error. Trial and error not in the sense that we tried every algorithm there was. We kind of took a baseline and said, okay, this algorithm does this, so this may be a better fit because there's no time or money to run every algorithm. So we ran about 3 algorithms that we thought were the best fit for the problem that we were solving. And then you have like deep learning, which I still don't understand, and I still don't, people always come and ask me, why aren't you doing deep learning? And they can't tell me why I should be doing this. So, but if anybody wants to try out, that's there. Data storage is another area that you really need to think about because it's not all SQL storage. SQL is a lot of overhead for some of these things. So you can have key store, flat files, document storage for the model storage and things like that. So you still have to kind of think about your database, your data storage, and how much data you want to store and how you want to store it. So I'm going to talk about two case studies. One is the traffic classification. Like I said, that's the one that we did. Traffic classification and fault detection were the two that we really spent a lot of time on. So what we did, we tested it on a small network with 250 to 500 devices. We did a port-based analysis, and it gave us about 70% accurate identification. We collected net flow from 3 different networks for 7 days in 30-minute increments. We did a lot of filtering and sampling. That was still a lot of data, and we didn't want to use all the data. So to get the spatial and temporal diversity, we sort of did sampling and filtering. And we did a 70-30 split, and we used the 3 algorithms to test it. So this is, if you can see, most of it is HTTPS traffic and some of the non-standard ports there. The port-based was not able to identify. And again, this isn't all the features we used. This is just a sort of a sampling of the features we used. And so we had provided the labels using the port base. So this many labels, and this was the precision and the recall. And the F1 score is a combination of precision and recall. Precision is how accurately it identified, and recall is how well it was able to remember. So if you see the Microsoft domain server, it wasn't able to recall, and we think it's because the number of samples was too small. That's another thing. There's a lot of explainable AI, explainable machine learning, and we did try to go back and see what it was learning and what it was doing, but there's still some of that black magic that happens that it's still hard to figure out. But we think that's because of the number of samples was too less. So the decision tree random forest and support vector machines, unfortunately, support vector machines did not give us any more accuracy than just port-based. I think it's just because the way the algorithm works wasn't really helpful for this. So decision tree and random forest were the two that gave us comparable results. So for the fault detection, we kind of did the same thing. Devices, networks between 200 and 500 devices. And we collected packet captures, and we basically sampled using 800,000 samples. We did not test support vector because we thought, since we couldn't even get it to work for a simple case, this was more complex. So we just decided to test with decision tree and random forests. So these are some of the features we used. Again, this isn't exhaustive, and a lot of it we took aggregation, we did standard deviation, we did coefficient correlation. This isn't just straight. We did have to do a lot of math in there to get. So this is sort of an aggregate of multiple streams over a period of time. And so this is what we found. So there was a threshold after which it wasn't learning. So what we realized, and we did this for a lot of different samples, and what we realized was it wasn't the number of samples that really mattered. What mattered was the quality of data that we fed into it. So as you can see, around 45,000, it tapers off, and after that it was basically a flat curve. So we had also sort of bought into this whole big data, throw as much data as you can at the algorithm and it'll figure out, and our experience was it wasn't if you can actually provide it better quality data, you can do it with a lot less than all the big data that you throw at it. But creating that quality data comes with a cost, so you either, I don't know, maybe if you put in a lot of data that eventually it'll kind of get there, but there's a cost involved in either one of them. So you have to pick where the cost is. So this is what we had for the events. So that's the big bar is the normal events, and these are all some of the fault and performance events that we said. One of the things that we found was we used some syslog data to kind of add to it, and that gave it a context, because unfortunately packet data, it gives you the network view, but it doesn't quite give you the server view. So we had to use some context from the server data to get like the server faults, if the server is functioning or server is malfunctioning, or if something's wrong because the server is the one that's down, not necessarily the network. The other thing that we were trying, again, I said the control plane telemetry, there's a lot of hype with streaming telemetry and everybody is doing, but we weren't able to get any useful data to actually test, but that's one of the things that we are kind of working on to see if we can get something to test it. It would actually help in some way. There was no real difference between the decision tree and the random forest in this one. So this should really be 5 slides. There's so many challenges. The biggest challenge was data collection. Data was very inconsistent, very messy, sparse. So trying to get the data that was useful was a lot of work. How to choose the right machine learning for a particular networking problem was also just trial and error. We tested with a small network, so how do you make it scalable to a large network? Maybe there is no way to scale it with what we have. Maybe we do have to do smaller segments of the network. I don't know, but right now I don't see a way to scale it to devices, 30,000 devices, and get any kind of result with it. So this was another challenge. How do you make machine learning models learn uniformly across non-uniformly designed networks? All of you who work in network design knows none of the networks are actually they're all designed differently. So how do you know that it's actually learning the right thing in each network? So that's another challenge. So some of the things that I would like to see, they're not necessarily future trends, and that's why there's a question mark. It's more like a wish list. It would be nice to have a more centralized data collection, especially data from different domains and different vantage points, instead of having to set up all these different data collection mechanisms. So hopefully SDN NFV might give us some path forward for that. It would be nice to have open data sets. I know that Qaeda has some, but it wasn't really that useful. We actually got data from customers, customer networks. It would be nice to have like standardized open data sets for specific problems. Feature extraction, like I said, that was a pretty tedious task as well. So it would be nice to standardize the training data set size and maybe even the features and say, okay, for this specific application, these types of features will give you the best result. It would be nice to have that standardized across different network applications. The machine learning algorithm robustness, that's outside the realm of really machine learning for networking. There's a lot of research going on in making the algorithms more robust and also making them more explainable to really know what it is learning. And I think it would be nice when we get there. I think that would help as well. There's automatic selection of the right algorithm. I know there is AutoML frameworks that Google has and some other things, but again, they all work for maybe more simplified data sets, not the complex data sets we have in networking. Again, combining ground truths and models from different vantage points is take different networks and standardize it and see what it means across multiple networks. Any questions? Anybody has any use cases? I would love to hear from you, or any way to use the data. But other than that, any questions? I may not have all the answers, but yeah.
I'm curious, to what extent is this a set it and forget it after you get the machine language model tuned? And to what extent do you have to babysit and keep going back to it? And how much time is involved on the ongoing basis?
This was done using historical, like we collected data over a period of time. So for you to really keep it adaptive, you will have to go back, because networks change, right? So let's say you add a new device, your traffic pattern will change. Hopefully the device gives you better performance. So you need to add that data and do incremental learning. So there's reinforcement learning that you'll relearn the model, but you're not relearning the whole thing. You're just incrementally learning.
Is it a full-time position?
Yes, probably. Yeah, it's just the network engineering position might be morphed into something else. So, yeah.
Dan McGorian, Johns Hopkins, APL, excellent talk.
Thank you.
Especially given where ML is on the hype cycle right now.
Yes.
On your last slide, why do you feel that SDN NFV what's going to help with your data collection problem? I didn't quite follow your logic there.
Because, and again, this is what I have been reading, is that once you have the control plane separated, most of the control plane data is going to be centralized. You're not trying to get data from the data plane anymore. Again, that may be in the hype cycle as well.
I think you're making some assumptions about what SDN is going to do for
Yes.
I haven't seen it help that much, at least in our case.
Yeah.
Thank you, though.
Ajay, Red Hat. So Srividya, is this product or the stuff that you're working for, is there any beta version of it? It sounds very interesting, right? But it also sounds like there's a lot of things that are not solved and is work in progress, right? And there seems to be a call to action to community to kind of help.
Yeah, and we do have a beta version of this, and one of the things is we're not trying to just throw some software at people and say, go figure it out. We want to actually work with the community to maybe build a framework and solve some of these challenges that we encounter to get some ground truths that it can actually help. One of the things is machine learning is not a magic button, but it does provide a new mechanism and pathway to address some of these problems as we saw. And we do need new ways to look at things.
So are there some resources that we could go look at, or is it still?
Most of the resources have been academic.
Okay.
And the problem with a lot of the academic papers is I don't think they are network engineers who are working on this. So, but I am trying to do more and educate people.
Thank you.
So. Okay, hold on, I think I'm out of time.